Welcome back to our channel. In today's episode, we're diving into one of the strangest and most fascinating ideas in all of science, quantum physics, the mysterious world where particles can be in two places at once, where observation seems to shape reality, and where the universe behaves in ways that almost feel impossible. But here's a question for you. Do you believe that reality might not exist in a definite form until someone observes it? It sounds like science fiction, but according to quantum physics, it might actually be true. Before we begin this journey into the strange and beautiful world of the quantum universe, make sure to subscribe to the channel so you don't miss our upcoming explorations, and feel free to leave a comment below sharing your thoughts. I'd love to hear what you think about these mind-bending ideas. Now, let's begin. Welcome to The Sleepy Scientist, where we embark on journeys through the most mind-bending corners of the cosmos, all from the comfort of your own quiet space. It truly is a delight to have you join us tonight. As we settle in, I'm always curious. Where in this vast, wonderful world are you tuning in from? Perhaps you're nestled in a serene bedroom, the day's worries gently fading. Or maybe you're on a tranquil train ride, watching the world blur by, a perfect backdrop for wandering thoughts. Perhaps you're curled up on a plush couch, a warm, comforting mug of tea steaming softly beside you. Wherever you find yourself, my deepest hope is that you are feeling completely comfortable, utterly safe, and perfectly poised to let your mind softly drift into the fascinating realm we're about to explore. If these calming explorations into the mysteries of the universe resonate with you and you'd like to journey with us more often, a simple like and a subscribe truly mean the world to this sleepy little channel, helping it gently float along. And to all of you who have already joined our quiet community, thank you. Genuinely, your unwavering support nurtures this space in ways you might not even fully comprehend. Now, I'll do my absolute best not to make tonight's topic so overwhelmingly interesting that it keeps you wide awake, battling against the encroaching night. But just in case it does spark an irrepressible curiosity and you find yourself pondering these concepts into the wee hours, at least you'll emerge with a profound understanding of why particles sometimes seem to shapeshift and act just like waves, and why reality itself appears to hold its breath, hesitating until someone finally observes it, a small intriguing price perhaps for a momentarily restless night. So, let's begin, shall we? What is quantum physics, really? And why, when we delve into its strange tenets, does it so often sound as if the universe is simply improvising its rules as it goes along, a cosmic comedian making up the script on the fly? The world we ordinarily perceive, the one we can definitively see, feel, and touch, impresses upon us a sense of unwavering solidity and absolute predictability. Here, gravity is an undeniable master. If you release a teacup, it will plummet. Chances a simple flip of a coin, it will land heads or tails. And permanence is an established fact. If you close your eyes, the moon does not in fact vanish from existence. Yet as the 20th century dawned, a new breed of scientists began to gaze upon this seemingly immutable reality, not just closer, but immeasurably closer. And the deeper they peered into the fundamental mechanics of matter and energy, the more astonishingly strange everything became. They unearthed a startling revelation. Light, that familiar illumination, possessed a perplexing dual nature, capable of behaving both as an expansive wave and as a discrete individual particle. Even more mind-boggling, tiny particles themselves, it appeared, could somehow inhabit a multitude of locations simultaneously, suspended in a state of indefinite existence until the very moment they were measured. And this act of observation, it turned out, wasn't merely a passive unveiling of what was already present. It seemed, in a profoundly unsettling way, to fundamentally alter the thing being observed. This wasn't some fleeting anomaly, a mere quirk of faulty data or the fuzziness inherent in imperfect equipment. No, this was demonstrably real, consistently reproducible across countless experiments. Wasn't just a discovery, it was a conceptual earthquake that utterly shattered the elegant, tidy, and centuries-old laws of classical physics, sweeping away the comforting certainty that had long governed our understanding of the physical world. Quantum physics wasn't simply a novel branch of scientific inquiry. It represented an entirely new lens through which to perceive the very fabric of reality. It presented a strange, shimmering, almost ethereal reality where the rock-solid certainty of the macroscopic world is replaced by the nebulous dance of probability, and where cause and effect, those bedrock principles of our experience, don't always unfold in the linear, predictable manner we've come to expect. In this video, we won't rush through this enigmatic world. Instead, we'll drift gently, slowly, allowing its mysteries to unfold at a comfortable pace. There's absolutely no need to wrestle with every complex equation or meticulously memorize every unfamiliar name. We'll navigate this landscape softly, deliberately, unraveling one captivating mystery at a time. Our journey will span from the earliest, most perplexing puzzles that first nudged scientists off their classical, comfortable perch, all the way to the modern, profound questions that continue to keep today's most brilliant physicists pondering deep into the night. So, take a moment to tuck yourself in, close your eyes if it helps you focus inward, and let's begin our exploration of a world where even seemingly empty space isn't truly vacant, and where everything you once believed to be undeniably true about reality is, well, probably true. As the 20th century gracefully turned, the scientific community, particularly in the realm of physics, exuded an air of profound accomplishment. It was a golden age of intellectual triumph, where the grand framework of classical physics seemed almost gloriously complete. Isaac Newton's laws of motion were meticulously understood, charting the predictable dance of planets and projectiles. Thermodynamics, the study of heat and energy, had been neatly organized into a cohesive theory, and light, that fundamental aspect of our perception, was elegantly nestled within the comprehensive structure of James Clerk Maxwell's electromagnetic theory, described as graceful, continuous waves. Many scientists of the era genuinely believed that all the monumental questions had in essence been answered. Only a few peculiar, odd bits remained, like small lingering specks of dust in the meticulously swept corners of an otherwise pristine, well-ordered room. One such dusty corner revolved around a seemingly innocuous and remarkably simple phenomenon. What precisely transpires when you heat an object? Observe any common material, a hefty piece of iron, a glowing ember of coal, and you'll witness it begin to radiate light, its color shifting from a deep fiery red through a vibrant orange, and eventually to a brilliant, almost blinding white, all depending on its escalating temperature. This radiant glow, scientifically dubbed black body radiation, is a direct consequence of how objects emit electromagnetic radiation when subjected to heat. It was effortlessly observable, a common occurrence, and thus it should have been straightforward to explain using the established tools of classical physics. And yet the meticulously crafted mathematics, the very foundation of this golden age, stubbornly refused to cooperate. Classical physics, employing the most sophisticated and well-regarded equations of the time, yielded a prediction so bizarre, so utterly nonsensical, it bordered on the absurd. According to these formulas, as the temperature of a theoretical black body, an idealized object that absorbs all incident electromagnetic radiation, steadily increased, it should emit an ever-increasing amount of energy at progressively shorter and shorter wavelengths, particularly spiraling into the high-frequency ultraviolet range. The cataclysmic problem? This mathematical projection inexorably led to a scenario of infinite energy at these high frequencies. Such an impossible and frankly ridiculous outcome was so unsettling that it quickly earned a dramatic nickname: the ultraviolet catastrophe. No amount of careful tweaking, no ingenious adjustments to the hallowed classical equations could prevent the math from spiraling into sheer absurdity. Reality, in its stubborn elegance, simply refused to conform to these confident theoretical predictions. Clearly, something fundamental was profoundly missing from their understanding. Enter Max Planck. The year was 1899, and Planck was a German theoretical physicist, renowned for his methodical, almost meticulous thinking. He was, by all accounts, not a radical firebrand, nor a rebellious iconoclast. In fact, he was deeply rooted in, and a firm believer of, the established classical worldview. But Planck was also an eminently pragmatic scientist, and when confronted with the intractable conundrum of the black-body radiation problem, he did something that, though quietly executed, was utterly revolutionary in its implications. Forcibly reconciled the unruly math with the observed reality, Planck introduced a small, almost ridiculously strange idea. What if energy, he mused, couldn't be emitted in just any arbitrary continuous amount? What if instead it came in tiny, discrete, indivisible packets, like coins that cannot be split in half, regardless of how much you try? These fundamental packets, he proposed, would represent the absolute smallest possible units of energy. He christened these mysterious packets quanta. This was a truly seismic shift from the prevailing continuous view of energy that had underpinned classical physics for centuries. Instead of envisioning a smooth, uninterrupted flow of energy, Planck's concept suggested that energy would arrive in distinct, abrupt steps, tiny, quantifiable jumps that were directly proportional to the frequency of the radiation being emitted. He even went so far as to introduce a new fundamental constant, now famously known as Planck's constant, h, to precisely describe the minuscule size of these energy packets. It was a number unimaginably small, yet mathematically elegant and astonishingly effective. When he meticulously plugged this daring new idea into his recalcitrant equations, something truly astonishing occurred. The vexing problem of infinite energy, the very ultraviolet catastrophe that had plagued physicists, simply vanished. The equations, once nonsensical, now worked perfectly. They precisely matched the real-world observations. Max Planck, almost by accident, had solved the ultraviolet catastrophe, and yet ironically he himself didn't entirely believe in the profound implications of his own solution. Planck candidly described his groundbreaking work as merely a mathematical trick, a clever, almost artificial way to compel the numbers to behave, rather than a genuine description of how the universe actually functioned at its most fundamental level. He held a strong conviction that future, more astute physicists would eventually uncover a superior explanation, one that wouldn't necessitate such peculiar, almost fantastical assumptions. To Planck, quantization was a temporary conceptual patch, a provisional fix, certainly not a fundamental, immutable truth. What he, in his humility, could not have possibly known at the time was that his unassuming trick would ultimately become the foundational cornerstone of an entirely new paradigm of scientific thought. His audacious idea that energy exists in discrete packets had unwittingly laid the intricate groundwork for what would soon be known as quantum theory, a theory poised to unravel, piece by unsettling piece, much of what classical physics had so confidently taken for granted. Looking back from our vantage point, it's easy to perceive this as the pivotal moment, the instant everything dramatically changed. But at the time, it felt more like an obscure, strange side note in a quiet academic paper published in 1900 rather than a thunderous revolution. Planck hadn't harbored any grand ambition to challenge the very foundations of physics. He simply wanted the stubborn math to finally make sense. And yet, by introducing the concept of quantization, he had, with quiet deliberation, ignited the very first match in what would become a slow-burning, inexorable fire, a profound intellectual inferno that would ultimately reshape our deepest understanding of light, of matter, and indeed of the very nature of reality itself. This humble beginning, tucked away within the pages of a scientific journal, didn't announce its monumental importance with dramatic declarations or sweeping, confident pronouncements. There was just a small, elegant constant, a subtly new way of conceptualizing energy, and a curious, ingenious little fix for a problem that had obstinately refused to disappear. From that pivotal point onward, the grand edifice of physics would never again feel quite finished. By the early 1900s, the scientific consensus held that light was a phenomenon largely, if not entirely, understood. Thanks to the monumental equations formulated by James Clerk Maxwell in the mid-19th century, scientists had convincingly demonstrated that light behaved as a wave, an elegant continuous ripple propagating through the unseen electromagnetic field. It exhibited all the expected traits of a proper wave. It bent around corners, diffraction, bounced off surfaces, reflection, refracted when passing through different media, and crucially interfered with itself, creating intricate patterns of peaks and troughs. And after Max Planck's somewhat unsettling yet effective introduction of energy quanta to resolve the ultraviolet catastrophe, most physicists optimistically assumed that things would soon settle back into a new, albeit slightly adjusted, normal. But then a stubborn riddle emerged. involving the interaction of metal and light and a surprising, almost defiant, refusal to conform to established wave theory. It was known as the photoelectric effect, and its basic mechanism seemed deceptively simple. If you shone light onto the surface of certain metals, electrons could be observed being ejected from that metal. The initial idea made perfect classical sense. Light, being a form of energy, transferred that energy to the electrons, effectively kicking them out. No big deal, or so it seemed. According to the prevailing wave theory, if you increase the brightness of the light, which equates to increasing the amplitude of the wave, you should logically increase the total energy transferred to the electrons. A brighter, more energetic wave should, in theory, shake electrons loose with greater force and in larger numbers. That was the confident expectation. However, experiments consistently revealed a completely different story. Scientists discovered something utterly perplexing. Shining brighter light didn't necessarily result in electrons being ejected with more energy, nor did it always eject them at all. What proved to be the crucial factor was the frequency or color of the light. If the light's frequency fell below a certain critical threshold, even an incredibly bright, intense beam of light would do absolutely nothing. Not a single electron was ejected. Yet above that specific frequency, even a remarkably dim beam of light could effortlessly knock electrons free, and with considerable energy. This threshold was incredibly sharp, almost like an on-off switch, and it defied every logical explanation offered by classical wave theory. This minor inconsistency rapidly blossomed into a full-blown scientific mystery, a gaping hole in the fabric of what was supposed to be a complete understanding of light. Enter Albert Einstein. 1905, a year that would forever be etched in history as his miracle year, annus mirabilis. Einstein, then a relatively obscure patent clerk, published a series of papers that would irrevocably alter the course of physics. One of these groundbreaking works was dedicated to explaining the baffling photoelectric effect. He proposed something extraordinarily bold, a concept that directly challenged the prevailing wave paradigm. What if light wasn't just a wave? What if, under certain specific circumstances, it also behaved like a particle, a discrete tiny bundle of energy traveling through space in a straight line? Einstein suggested that light itself was composed of individual packets of energy, which he initially termed quanta of light, directly building on Planck's idea, later to be famously known as photons. Each of these photons, he posited, carried a very specific fixed amount of energy, an amount directly determined by its frequency, its color. His explanation was elegantly simple. If a photon possessed enough energy, ELIE, if its frequency was high enough, it could deliver a sufficient punch to dislodge an electron from the metal surface. If, however, a photon's energy was below that critical threshold, then no amount of photons, no matter how numerous, no matter how bright the light beam, could accomplish the task. It was, he famously illustrated, akin to trying to open a locked door. You could have a vast handful of keys, but if none of them fit the lock, you simply weren't getting in. Quantity didn't matter. Quality, the energy per photon determined by frequency, was everything. Einstein's revolutionary idea didn't just borrow from Planck's earlier reluctant work, it dramatically extended it. Planck had used energy packets as a mathematical convenience, a trick. Einstein, however, was asserting that light itself was literally made of these packets, not as a helpful fiction, but as a fundamental physical description of how light intrinsically behaves. This was a profoundly revolutionary claim, and understandably, not everyone embraced it. Many established physicists, having devoted their careers to the elegant wave model of light, clung tightly to it. After all, light clearly exhibited wave-like behavior. It diffracted around obstacles. It created those intricate interference patterns, much like ripples in a pond. If light was genuinely composed of particles, how could it possibly simultaneously behave like an expansive wave? Einstein, in his characteristic brilliance, didn't deny the well-established wave nature of light. Instead, he proposed something even stranger, a concept that would become a cornerstone of quantum mechanics. Light, he declared, was both a wave and a particle. It could manifest as one or the other depending entirely on how you chose to observe it, on the nature of the experiment being performed. This wave-particle duality wasn't merely a curious trick of perception or a limitation of our measuring devices. It was, he argued, fundamental to the intrinsic nature of light itself. Imagine a simple beam of sunlight filtering through a window, spreading and rippling elegantly as a wave, bouncing off microscopic dust motes and refracting through the glass. But then zoom in, infinitely close, and you would find yourself face to face with countless tiny individual quanta of energy, photons, each with its own specific frequency, colliding with atoms, imparting energy, and subtly changing the world, one discrete collision at a time. This profound idea of wave-particle duality remains one of the most unsettling and counterintuitive concepts in all of physics. Not because it's mathematically complicated, but because it challenges the very foundational categories, the very linguistic structures we employ to describe reality. In our familiar classical world, things are unequivocally either particles or waves, never both, never neither, and certainly not shape-shifting entities that decide their nature based on the circumstances of observation. But the quantum world, it seems, doesn't feel compelled to ask our permission to make sense. Einstein's photon-based explanation of the photoelectric effect not only perfectly matched all the perplexing experimental results, it did so with breathtaking elegance and simplicity. The energy of each photon directly depended on its frequency, exactly as Planck had earlier suggested, and this neatly explained why low-frequency light, no matter how intense or bright, couldn't eject electrons. The individual photons simply didn't carry enough energetic punch to overcome the atomic binding forces. The ramifications of this idea were truly monumental. In 1921, Albert Einstein was awarded the Nobel Prize in Physics, not, as many mistakenly assume, for his theory of relativity, but specifically for his groundbreaking explanation of the photoelectric effect. That's precisely how significant and paradigm-shifting this particular discovery was. Still, even Einstein, the very architect of this revolutionary concept, found the emerging quantum world deeply uncomfortable. He famously resisted the more radical probabilistic interpretations that would follow in subsequent years, declaring with a poignant mix of frustration and conviction, God does not play dice with the universe. But whether by divine hand or cosmic happenstance, the fundamental rules were undeniably changing. And at the unsettling heart of those changes lay a strange and beautiful truth. Light, the very medium that illuminates our entire world, steadfastly refused to fit into any tidy, conventional box. It arrived in discrete quanta, yet it danced and rippled as a continuous wave. It collided with matter like a solid particle, yet it shimmered between states, revealing just enough to perpetually fuel our wonder, and just enough to keep us forever unsure of its true, singular nature. What began as a seemingly straightforward experiment with light and metal ended up sending shockwaves through the very bedrock of physics, because if light could behave in such an impossibly dualistic fashion, both continuous and discrete, both spread out and point-like, what other profound, rule-breaking secrets might be quietly lurking in the universe's unseen corners, patiently awaiting their moment to redefine reality? Imagine this seemingly trivial setup. You arrange a sturdy table, placing a modest flashlight at one end. In the middle, you position a piece of opaque cardboard into which you've meticulously cut two tiny parallel slits. You then switch on the flashlight, directing its beam through these narrow openings, and observe the pattern it projects onto a screen placed behind them. Not exactly the stuff of thrilling scientific drama, right? And yet within this utterly humble arrangement, just two holes and a sliver of light, we uncover one of the most profoundly mind-bending experiments in the entire history of science. The double-slit experiment has over time ascended to the status of legend in physics, and not because of any inherent complexity. In fact, it's almost embarrassingly simple in its execution, but what it unveils is anything but. Some physicists with a wry sense of humor have even half-joked that this might just be the most dramatic science experiment of all time, starring nothing more than a simple flashlight and two strategically placed holes in a piece of cardboard. Let's first establish what our classical intuition, grounded in the macroscopic world, would confidently predict. In the familiar realm of classical physics, waves and particles behave in fundamentally distinct ways. Wave, much like ripples expanding across a pond or the sound waves carrying our voices, spreads out. Its energy isn't localized, it's distributed, and critically, it interferes with itself. Picture ocean waves encountering a breakwater with two narrow openings. As the waves pass through these openings, they emerge on the other side and begin to overlap. Where the crests of these new waves meet, they reinforce each other, creating higher peaks. Where a crest meets a trough, they cancel each other out, leading to areas of calmness. This phenomenon, known as interference, produces a characteristic pattern of alternating strong and weak or bright and dark bands. It's a well-understood, entirely predictable outcome of wave behavior. Now, contrast this with particles. Imagine firing a rapid succession of tiny rubber balls at the same wall, also equipped with two openings. Each ball is a discrete entity traveling a distinct path. Some will pass through the left slit, others through the right. They are consequently on the screen positioned behind the slits. You would unequivocally expect to see two distinct clusters of impact points precisely aligned with where the slits are located. This is the epitome of particle behavior, straightforward, localized, and utterly devoid of surprises. So, what happens when you perform this experiment with light, that enigmatic entity we now understand to be both wave and particle? When scientists first shone a continuous beam of light through the two slits, they expected it to behave like a wave, and indeed it did. The light spread out beyond the slits, forming an unmistakable interference pattern, a series of distinct bright and dark bands on the screen caused by the light waves reinforcing and canceling each other at specific locations. So far, so good. Light, as Maxwell had predicted, was behaving exactly like a wave. But then things took a decisively strange turn. Using incredibly sensitive equipment, researchers meticulously reduced the intensity of the light source, dialing it down until it was emitting light one single photon at a time. Instead of a continuous stream, individual particles of light were now making their solitary journey toward the slits. At this point, classical intuition would lead us to expect these lone photons to act purely as particles, each making an independent choice, either passing through the left slit or through the right. And if you patiently waited long enough, accumulating thousands upon thousands of these single photon hits on the screen, you should, by all classical logic, observe two bright spots precisely where the particles landed, just like those rubber balls. But that's not what happened. Astonishingly, even when sent through one by one with significant time gaps between each, the photons gradually, inexorably began to build up the exact same interference pattern as before, a pattern that fundamentally requires waves interfering with themselves. The paradox was immediate and profound. How could a single photon interfere with itself? Did it somehow pass through both slits at once? Was it simultaneously an ethereal wave and a localized particle? This wasn't some optical illusion or a trick of the eye. The interference pattern stubbornly persisted, suggesting that each solitary photon had in some unfathomable way explored both paths simultaneously, like a ghostly probabilistic